Good morning everyone. Today I would like to discuss a problem on Green's theorem. Before of discussing of a problem, I am giving the statement of the Green's theorem. In the Green's theorem, we discussed the transformation of the line integral to the double integral in a plane. Okay. Here the statement of the Green's theorem is Green's theorem in a plane. In the Green's theorem, the relation in between the transformation of line integral to double integral. In this case, let capital R be a closed region in xy plane enclosed, bounded by a simple closed curve, closed region bounded by a simple closed curve, simple closed curve C, and M and N or continuous functions of xy plane, x and y variables having continuous derivatives in capital R, then the line integral closed curve C m dx plus n dy is equal to double integral over region capital R dou n by dou x minus dou m by dou y into dx dy. This is a statement of the Green's theorem. Here, that is the relation in between the line integral and the double integral. The line integral means the curve is a simple closed curve, that is a curve C, and here capital R means that is a xy plane, that is a region is in xy plane that is bounded by a simple closed curve. That is nothing but we are taking, it is x-axis, it is y-axis, then any curve is bounded in xy plane with the simple closed curve C. Then by using of this relation, we can calculate the region of over R in xy plane, and the function is in m and n functions, both are defined in the xy variables. Those variables are also continuous derivatives in capital R. Then the Green's theorem is integral over C, that is a line integral in a simple closed curve C, m dx plus n dy equal to the double integral means the region capital R is in xy plane, means one integral for x, another one is for y. Then dou n by dou x minus dou m by dou y into dx dy. It is the statement of the Green's theorem. By using of Green's theorem, we can find out the verification of the given problem. That is nothing but we can prove that LHS is equal to RHS by using of the relation of the given curve, and that curve is bounded in a closed region capital R with the limits. By using of those conditions, we can calculate and verify the Green's theorem. that is integral over C m dx plus n dy equal to double integral of r dou n by dou x minus dou n by dou y. If it is in circular motion, then that is integral over C f dot dr is equal to integral m dx plus n dy is equal to 0 n dy. That is nothing but here f bar is equal to m I plus nj, dr bar is equal to dxi plus dyj. We know that r bar is a position vector, that is xi plus yj. If it is in circular region, then the position vector is xi plus yj. In that region, the circular means I and j are the unit vectors along x-axis and y-axis. Along x-axis means the function m is the in xy variable, n is also in xy variable. Those are represented as the x and y axis. Then f dot dr is equal to multiplication of these two, I dot I, that is equal to 1. Then it is m dx plus n dy. By using of these relations, we can prove that and we can verify the Green's theorem. If the curve is in a simple closed curves that is bounded with the region in xy plane, means directly we can take m dx plus n dy. The given integral is comparing with the m dx plus n dy, in that what are m and n functions. By taking off those functions and differentiating with respect to x, n function with respect to x and m function with respect to y, and taking the limits. By giving the curves, we can find out the limits and we can prove that and verify the Green's theorem in the normal curve. But in the circular motion means we can take f bar is a function in a circular region that is indicates as the vector form, that is mi plus nj. Here m and n are the functions in xy variable, and here the r vector is the position vector of xy plane. So that r vector is equal to xi plus yj. That x is represented as a x-axis, y is y-axis. Further, the derivative of position vector is equal to dxi plus dyj. In the circular curve, then the line integral is equal to f bar dot dr bar. That is nothing but both are vectors. In the vectors, we can take dot product. Then that is equal to the closed curve C. It is in x and y variables with the continuous derivatives, that is m dx plus n dy. Then as usual we can take m dx plus n dy comparing with the m and n functions and taking the derivatives with respect to x of n function, y of n m function, and differentiate. Then we are getting the function, and in that one integral is x limits, one integral is y limits. By using of that relation, we can verify the Green's theorem. Okay, it is the theorem statement and how we can verify the Green's theorem by using in two different cases. One is a simple curve, another one is in circular motion or circular form of the curve. Okay, thank you.